So good afternoon everyone, and first I would like to thank the organizer for providing me this opportunity. And today I will talk about our recent work, the tracer dynamics in hard.gas, that has been done in collaboration with Seema, who is a PhD student here at ICTS, and Anupam Kundu, Abhishek, Dhar, and Harvard Spawn. So the hard-dot system is a simple yet non-trivial example in the context of the classical integrable system. So here we consider, let's say, n number of hard dots, each of length a and of unit mass, that moving on an infinite line, let's say. And this restriction basically says that the two hard dots, they cannot come closer to this distance say. Now, these hard dots, they move ballistically in between two successive collisions, and once they come together, if they collide, their moments are kind of exchanged. So as their moments are only exchanged in this system, so all the moments of the moment are kind of conserved. So these all are the conserved quantities here for different values of alpha. So now if we see the dynamics for this rod, so if these two rods, if they did not collide, so the black one follows this dotted one and the red one also follows this dotted one in the non-interacting picture, because but in the due to the collision, ultimately the red one goes like here and the black one goes here. So what it means that upon one particular collision, the rod, it jumps over distance a, which is equal to its length. So now, as in each collision, the moment is only kind of exchanged. So it is possible to follow the trajectory of one particular rod with some specific velocity. Now, the trajectory effectively represents the dynamics of a quasi-particle that moves ballistically with a specific velocity and punctuated by some sudden jumps during the collisions. And in the context of hard-dot system, the quasi-particles are essentially the velocity tracers that jump from one rod to the another during each of the collision, and such that the tracer rod, they follow a given momentum. So the natural question that can arise that how this tracer rod, they move in time. Okay, so for that, in the hard-dot system, we first take one particular hard dot with some particular velocity, let's say v naught. This is generally called the tracer rod or maybe the quasi-particle. And if we follow its trajectory, the trajectory here, this red dashed line. So if this rod, it did not interact, it follows this path. But due to the interaction or due to the collision with the other dots, in every collision it jumps and finally it goes like here. So what it means that there is this kind of extra displacement in addition to the displacement due to its drift velocity v naught. And this and the number of jumps due to the collision, it fluctuates from one configuration to the another, and this fluctuation effectively gives rise to the spreading of the distribution of the tracer collision. Okay, so now in this today's talk, we basically discuss the dynamic of the tracer rod, how it moves in the background of the other hard rods. But before going to our case, the hard-dot system or maybe the tracer dynamics, it has been studied extensively using the hydrodynamics approach, where the hydrodynamics can be written in terms of the phase space density of the quasi-particles. And in the hydrodynamics, the Euler GSD or maybe its correction, it can successfully describe the mean density profile. Whereas if we want to study the correlation between or the fluctuation between the two tracer particles, then this Euler GSD it cannot describe, and one requires the description of the fluctuation of the phase space densities. And usually in the conventional hydrodynamics framework, one uses the Landau-Lipschitz theory, but it also fails to describe in the context of integrable system. So in the context of integrable system, the studies on fluctuating hydrodynamics theory is kind of limited. And recently there is a study by Ferrari and Ola. So for hard-dot gas in equilibrium homogeneous mass density, so they studied it with the fluctuating hydrodynamics framework. And in particular for two tracer rods moving in the background of the other rods. So for that system, they obtained the fluctuation for the microscopic phase space density, and that evolves like this kind of stochastic partial differential equation, where this diffusion constant is characterized by the variance of the tracer position with velocity v, and this term it appears in the correlation between them, and also it can be written in terms of this diffusion constant. But this study is based on the homogeneous framework. Okay, so now here we want to provide an exact microscopic derivation for the variance and the covariance for these tracer rods, and not only for the homogeneous, for any generic initial density profile. So for that, we first considered single tracer rod that moving in the background of many hard rods. So we considered tracer rod with velocity v naught, and for this single tracer rod, there are the earlier studies by these people, both using the hydrodynamics or the microscopic approach, and all of them they basically said that the distribution being Gaussian at late time. And one can see that the variance for the tracer rod is directly proportional to the diffusion constant that can be characterized by the velocity for the tracer rod. And as this variance can be written is proportional to the diffusion constant, so it kind of it moves like a Brownian particle. So to get more evidence, we also compute the position autocorrelation for the single tracer rod. That is the correlation for single tracer rod position at two different times. So let's take this initial condition, initial configuration for the, this is a tracer rod at velocity v0, and during the time evolution at time t1 it be at x1, at time t2 it be at x2, and we want to compute the connected two-point correlation function. So using microscopic approach, we computed this connected two-point correlation function, and we obtained that this is proportional to the diffusion constant, which is similar to the two-time correlation function that of a free Brownian particle that one can compute. So what it means that the tracer rod in the background of the other rod, it effectively moves as a Brownian particle. So now the question is that in our system, if there are more than one tracer rod, so then how the motion of one tracer rod, it will be get affected by the another one. So that we want to study now. So for that, we consider two tracer rods. One is velocity with V0, another is U0. And initially they are separated by some microscopic distance, let's say Y0. And then we time evaluate our system. And using the microscopic approach, we can compute the mean and variance like that. And here we see that the variance for the individual tracer rod with velocity V0 and U0, they're directly proportional to the diffusion constants. And also we compare it with the numerical simulation. So the solid lines are from the exact and that match with the numerical thing. And here the main plot is for homogeneous and the inside is for inhomogeneous density profile. But the interesting thing is that here for both the tracers, the variance is proportional to the diffusion constant, which is similar to the Brownian particle. So it means that in this for two tracers also, they individually exhibit the Brownian-like motion. So now what we know for two Brownian particles, that if they evolve in some chaotic movement, then ultimately it converts to two independent Brownian motions. So that we know. So the question is that as we discussed that individually the tracer exhibit the Brownian-like motion, so one can generally expect that the tracer will they follow the same behavior or not. So then one can expect that it will follow the same behavior. But the question is that is it so much obvious or is it true? So for that we calculate how the separation between the two tracer rods that evolves over a time and how their fluctuations are kind of correlated. So first, for that we compute the covariance between the position of the two tracer rods in terms of the diffusion coefficient, and also we compare it with the numerical results. And following the description for the variance and this covariance, one can compute the variance for the separation between the two tracers' position. So what we see that this tracer rod that's moving in homogeneous background density and with equal velocity, the mean of the separation is kind of constant. Why not? Recall that Y0 is the initial separation between the two tracer rods. But the interesting thing is that the variance of the separation, the diffusive scaling limit, it goes to 0. So what it means, the fluctuation of the separation that does not grow even if the variance of the individual tracer rod, it grows linearly with time. And the motion of the tracers that become increasingly correlated, and they move like collectively like a rigid body like that. So these are the two tracer rods, they move like this kind of rigid body with a fixed separation. So this is also similar to what Ferrari and Ola claimed using the hydrodynamics approach in their paper. And ultimately, the motion of these two tracer rods, they converge to the same Brownian motion, which is in contrast to our common belief that what we know about the two Brownian particles. Okay, so in addition to that, we have also phenomenologically derived the fluctuating hydrodynamics theory in this case. So as we discussed that for the hard rod system, if we take a quasi-particle of the tracer rod, the red one is let's say the tracer rod. So as it behaves like a Brownian motion, so one can write the effective equation of motion, but this xi is the stochastic white noise. Just 1 minute. The stochastic white noise that with zero mean and the fluctuation on the correlation can be written in terms of this diffusion constant. And here also we can find the macroscopic fluctuation, the phase space density. It follows this kind of stochastic differential equation that is similar to what obtained by Ferrari and Ola. So this is a summary. So we studied the dynamics of this tracer rod moving in the background of many hard rods using the microscopic approach. And we exactly computed the mean variance and covariance of the tracer rod. And following the variance, though we see that individually both the tracers, they move like a Brownian particle, but effectively they perform like a strongly correlated Brownian motion, which is in contrast to the motion of two quasi-particles in chaotic environment. And this correlation makes two tracer rods with same velocity move effectively like a rigid body. So thank you.
Any questions?
Hi. So if I think of them as, the tracer rods are just coupled to a common path, right? So in some sense, since they're coupled to the same path, it's not surprising that they're correlated, right? The point is, I would think that they should be correlated if you think of these two tracer rods are in a path of other hard rods. And the path is common, so it's like taking two particles that are coupled to a common environment, so they will get correlated to the path, right? Or am I misunderstanding something?
No, what we wanted to say that our point is that though they individually follow a Brownian motion in the kind of hard rod system, but eventually they will go like that. They will be strongly correlated. Their mean position will be like same, and they will move like this kind of thing.
Yeah. So they individually are going to
individually follow the Brownian.
But together, when they're there together, I would imagine that they should be correlated.
Yeah, they are correlated.
So, but you had written that, I mean, so it is expected to be correlated, right? So it's
No,
not surprising that it is correlated. It's
no, why
expected to
it
be
is,
correlated, no?
it should be.
Because they are in the path of other hard words. Maybe I'm misunderstanding some point, but I mean, I would expect them to be correlated. No?
Okay, so we thought that because of the two Brownian and as the two Brownian motion that can be independently that evolves like large time. So we thought that they move, they should be correlated, but they should be independent. But here is kind of correlated, so that we wanted to. Okay, so maybe
Okay.
we can discuss.
There are these the two tracer rods. What will be the number of other rods in between them? Will that fluctuate or will that
Oh
remain?
yeah, so that we have, yeah. So we also computed, to understand this, we also computed the fluctuation of the net flux, that is the net number of rods that entering between the region between the two tracer rods, or maybe the fluxes of the rod or the current. So we computed the joint distribution for the J1, J2, which is the current for tracer rod 1, tracer rod 2 at any time. So this is for any particular time. So here we see that this kind of, you see that for any time the J1 is equal to J2 for this case. So they are kind of correlated. So J1 and J2 are kind of same.
But they vary between -70 to +20 or whatever. No, -90 to -50.
We should get a kind of straight line, but here also maybe we have to go for large time because this is an in the diffusive scaling limit. But actually we want to see that the current that suffered by the tracer 1 or the tracer 2 is kind of same. So it means that eventually the number of the net fluctuation for the the number of dots that entering between these two would be there will be no fluctuation. So that we wanted to see from here.
If there are no more questions, we'll thank the speaker and break for lunch.